So guys, to my memory, this is where we left off. And I think I'm right, so this is where we're going to pick up. And so I'm getting the sense that sort of this transition is going to be difficult because we're really concerned about calculators and things like that. So I don't know what I need to do to re-engage you with the conversation. But if you remember, guys, the term that I use, conversation, is not that teacher term that teachers like to use when it's just the teacher doing a lot of talking and you doing a lot of note taking, and we pretend it's a conversation because something makes us feel guilty about just spewing information for an hour. Guys, it literally was a conversation. If you remember, we got through 3 slides yesterday, last time. And it really was, and you may remember me reinforcing the way you guys handled this, it really was a conversation. That I was simply throwing up things on the screen that became the topic for your guys' questions. And we had some interesting conversations about acids and bases and conjugates, and this idea that water is no longer going to be a passive bystander in the aqueous chemistry that we're going to talk about. That water is fully an acid. It contains hydrogen. It's fully a base. It contains OH. And we are going to strategically learn to include or not include the water depending upon our particular needs. So that is a starting point. We got to the bottom. And guys, you may remember that in order to get to the bottom of this conversation, we had an important thought that we planted, which was the answer to the question, what makes a strong acid a strong acid? Do you remember? So what makes a strong acid a strong acid? And yes, by definition, it means it completely dissociates. That's the definition. But now we understand more than the definition. We've gone beyond what a strong acid is, and we've now talked about why are those 7 acids strong. And what did we conclude? Are, but what's the word? We're going negligible. So guys, is that ringing enough that we can just count that as part of our understanding, or do we need to dwell and reinforce? I don't ask that rhetorically. Are we okay? And you'll tell me if you're not, right? So we understand that the 7 strong acids have conjugate bases that are incapable of taking hydrogens away from hydronium, and consequently they don't drive backwards, and so there is no equilibrium that's reached, whereas with the strong acids, their conjugate bases do function as bases and push the equilibrium in both directions. Is that okay? We're good? We're good. We're good? We're good? We're good. We're not good. It is. Yeah. Thank you for asking. Are we good? All right. So guys, this we've talked about. Let's remind ourselves there's one little thing that we need to do before we get into some of this idea of water no longer being a passive player in aqueous chemistry. I don't think you need to write this down, but let's talk about it quickly. And guys, seriously, don't write it down. But let's talk. So if we have this balanced equation where HNO3 nitric acid is going into water. We know that acids form hydronium ion, and we know that NO3 then would be the conjugate base. Let's name our participants. So guys, what does that make HNO3 if it's losing hydrogens? The acid. What does that make water? The base. And we understand that water can be a base. Now let's pick up our conjugates. So guys, in order to find our conjugate base, we go to the acid, we remove a hydrogen, that makes nitrate our conjugate base. And maybe now we could reinforce what we learned last time. What do you know about nitrate's ability to function as a base? It's negligible. It's worthless. If you don't understand that, you allowed me to go forward too quickly. Because guys, this is the point. Nitrate has no ability to pull a hydrogen off of the hydronium and move this equilibrium backwards. You ready for an interesting thought? Why can't nitrate pull a hydrogen off of the hydronium ion? Not IMFs. Let me do this. It's not electronegativity. Does that help? Lewis dot structure for nitrate. Understanding this is not the Lewis dot structure for nitrate. Delocalized pi bonding. Guys, it turns out, and what do we call those structures that contain delocalized pi bonds? Resonance stabilized molecules. And guys, the reason that we call them resonance stabilized molecules is literally this resonance reality that they do makes them more stable. And so this ion, NO3, because it contains delocalized pi bonding, it actually stabilizes the molecule in a way that allows it to be stable without the hydrogen that it originally had over here. And as a result, it is a negligible base because the resonance, the delocalized pi bonding, stabilizes it, keeping it from being able to steal a hydrogen. Guess what? Acetate does that too. We'll talk more later. But it forms weak acids. So the rules don't always apply, but it does in this case. Okay, so now guys, let's go here. Acid-base conjugate. Don't write it down, just do it in your head. What is NH3? What is water? What is NH4 plus? And what is OH? You got them in your heads? Okay, so guys, now what is NH3 doing? Gaining or losing a hydrogen? Gaining a hydrogen. What does that make NH3? A base, so that makes water the acid. Now let's do our conjugates. What does that make ammonium ion? Our conjugate acid, and hydroxide is our conjugate base. And now guys, we get to this interesting point which we talked about last year. Which one is it? Here, water is a base. Here, water is an acid. Which one is it? It's both. What do we call it? Amphoteric. So guys, if you do not remember what amphoteric means a substance that can act as either an acid or a base. If you need to write it down, knock yourselves out. No, we talked about, do you remember, didn't we talk about that last time? Yeah, were you not here? Or maybe you were here and don't remember. We talked about, in particular, did we talk about H2PO4 minus? Do you remember? And it can give or take hydrogens. Another one that does this a lot is the bisulfate ion. Actually, it's wonderfully amphoteric. This is the stuff that I use to pH balance my hot tub, is sodium bisulfate, because the bisulfate ion can act as an acid or a base. And so it does a really good job of holding pH because it can function as both. I'm seriously convinced that the only reason I have a degree in chemistry is to keep my hot tub clean. Like, do you guys, any of you have, we've talked about this, never mind. It's like full on crazy trying to keep a hot tub balanced. You guys good? Y'all caught up with me? Okay, so now guys, you ready for a deep thought? This is interesting, and I'm going to show you a slide in a second, but think about this. So we just had this conversation that says that water can be both an acid or a base. But now guys, look at this. This is an acid, right? Why did we call that the acid? Because it lost hydrogens to what? Water. What is this? A base. Why did we call it a base? Because it receives hydrogens from water. So guys, you ready for a deep thought? What makes an acid and a base a base? The answer is it's always compared to water. Substances that we consider to be acids are acids because they're better at giving away hydrogens than water. Water is actually our 0 point, and we're going to talk about this more in just a second. But when we call something an acid, what that actually means is it's better than giving away hydrogens than water. And when we call something a base, it means simply that it's better at taking in hydrogens than water. Water actually becomes our fixed point. To help you see this, check this out. So guys, we understand this, right? I don't think you need to write this down. Strong acids completely give away hydrogens. Weak acids partly ionize. And then we talked about these acid-base parent conjugate relationships that say the stronger the acid, the weaker the conjugate base, and vice versa. Well guys, all of that is summed up here. I think this is still in your book. But if it's not, guys, this is a continuum of acid-base strength. And I want to give you a second to just sort of soak it in. And then, guys, we're going to talk about this. This is interesting. Can we talk? So, guys, it goes like this. First of all, notice the extremes. The extremes are the strong acids and the strong bases. And I want to be able to write, so I'm going to grab a pen. But guys, this is the interesting interrelationships between all this stuff. So the idea is this, that we have this idea that we've got strong acids. And when we have strong acids, we understand that the acids that are strong have bases that have conjugate bases that have negligible strength. So they have no ability, worthless ability, to take in hydrogens and function as bases. But guys, all of these, the strong acids, are actually better at giving away hydrogens than hydronium ion, and consequently are better, their conjugate bases are worse at taking in hydrogens than water. And so water actually provides our 0 point, if you will, on both ends of the scale. So when we say something is a strong acid, what we're saying is it's better at giving away hydrogens than hydronium ion, and as a result, it will overpower water and turn it into hydronium. But now, guys, the thing that's interesting is this. This is not surprising. Hydroxide ion is a strong base, right? And we understand that because the group 1 and heavy group 2 hydroxide salts are our strong bases. But guys, that's not it. It turns out that there are other substances that are actually strong bases, including, interestingly, actually it's on the other side, my bad. I'm drawing in the wrong place. Actually, these guys. So oxygen, hydrogen, and hydronium are all better at taking in hydrogens than water. And so those things all function as strong bases. This explains why OH is a strong base, but there are other things that are as well, including hydrogen ion, or hydrogen negative ion, and CH3 minus. But guys, we don't worry about those. So the only one that you really need to know for the strong bases is just OH. Yeah. Yeah, it's a good question. Let me just draw. So we are looking, so for example, here we've got HCl and here we've got HF, right? And it's interesting because the negative ion is a halogen in both cases. And so why the difference? But we could even ask a bigger question and say, what about iodine and bromine? Because those make strong bases as well. And maybe we should say this list isn't exhaustive, right? How many acids should be up here? 7. Oh gosh, don't touch the board. So there should be 7 up there. So why is it that HCl is a strong acid but HF isn't? So I'm going to get you halfway to the answer and then say we're going to talk next time. So what does it mean that HCl is a strong acid? What does it do? Completely gives away hydrogens, right? What does it mean that HF is not a strong acid? Doesn't completely dissociate. But the thing that's interesting is these are both very, very simple molecules, and they are molecules. So these are covalent bonds. So what do we know about the bond, the covalent bond between hydrogen and chlorine? It breaks apart like crazy, and it gives away hydrogens. Well, what about the bond between hydrogen and fluoride? Well, it turns out that this bond doesn't break as readily. And consequently, it makes it a weak acid. Now the question is why? You're going to find out next time. The answer is because of the polarity of the bond. That that fluorine is so electronegative that bond is actually strengthened by that polarity. And we're going to talk all about that next time. So for right now, just understand it has to do with the bonds that form between the hydrogen and the other thing. And we're going to put a much finer point on that next time. So if you're looking to dig deeper into this, I'm going to ask you to wait, but go ahead if not. Mm-hmm.
All the other elements, like let's say nitrogen, like nitrogen donor, nitrogen like acceptor, like why don't we do like?
Yeah, right. So why are we so caught up on hydrogen, right? Yeah, and I don't know that I can provide you a great answer, but I mean, it's sort of metaphysical, but it's an interesting question, right? And right, because water is the foundation of what we do, and hydrogen is the most plentiful element in the universe. And I mean, creation, evolution, however you sort that out, understand that a lot of the original chemistry was simply driven out of biology, that we were trying to understand life and processes and systems that we see here on Earth. And so many of those systems are simply hydrogens getting pushed around. And so looking at hydrogen concentrations became very useful to us. Understand that there are chemists that look at nitrogen concentrations, and that's not my board, you can figure out PN, which would just be the negative log of the concentration of nitrogen. We don't talk about it much, but there are chemists that do other p-values looking at other concentrations. It just isn't generic enough for us to think about it, because really a lot of what we're doing in here is just to feed an understanding of biologic systems. So, you guys good? You okay? You're traveling light. Do you need stuff, or are you okay? Are you? Oh, no. Are you okay? Okay, we're glad you're here. Yeah? Hold on, do you mean hydronium or hydroxide? If I'm saying hydronium, I mean hydroxide. Did I say hydronium? Okay, scratch that, reverse it. No, not so hydronium. So hydronium is our reference for strong acid. Hydroxide is our reference for strong base. Is that okay? You guys okay? Go ahead.
With OH, why do we even I see why it's the base, because it's able to accept it.
Exactly.
On the negligible side of the acid, does that mean is it because OH in theory could give off another H and then go to
But it just doesn't. Exactly. Right. And that's exactly why. Yeah. Are we good? Good? Okay. So guys, not really review, but kind of. We have looked a little bit. pH. I've shown you graphs like this that are sort of pH-like. So guys, what we're going to do now is we're going to sort of move into the things about acids and bases in water that we haven't talked about. Up until now, we've talked conjugates, we've talked Arrhenius, we've talked Bronsted-Lowry. We've done a lot of that stuff. Now what we're going to do is begin a conversation that we haven't had before. So this is probably where you're going to want to start getting these things in your notes. This is where this gets interesting. So our transitional thought is this. Water is amphoteric, right? It contains hydrogen that makes it an acid. It contains hydroxide that makes it a base. Based, no pun, on that idea, guys, we're now going to talk about what is called the autoionization of water. You're about to have an aha mathematical moment. Oh, by the way, guys, this would be a good time to grab your AP equation sheets. If you don't have one, Brandon will lend you one of his 12. Does anybody need one? You guys good? You still have the original? Whoa. Nice. Anybody need one? You guys good? You good? You're good? Do you need one? Oh, you're good? You want two?
Wait, I just lost mine.
You realize if you just lost it, you would actually have it. Oh boy. All right. So guys, autoionization of water. If you write an autobiography, who writes the story? You do. Auto means imposed upon yourself, right? So do this with me. Water is amphoteric. Guys, consequently, it can react with itself. So here's what I'd like you to do. Write the balanced equation, acid-base reaction, for two water molecules. Write them separately. Don't put 2H2O. So H2O plus H2O. Write the product for that reaction, which is the autoionization of water. Yeah, if this were not an equilibrium process, we'd all be dead. Because we'd have no water.
Plus, why would it not?
And that's what you're representing. So, are you done? Did you all get this?
I used that.
So, guys, what we have here are two water molecules, and maybe it might be interesting and helpful for you to picture this, but what we're representing here is two water molecules interacting with each other. And well, this isn't great because I can't pick these apart. And this probably doesn't have what I need. Yeah, can you picture it, or do I need to show you? Okay, so you can picture it. No, I don't have a video for this. But what you've got here, guys, is two water molecules that come, oh wait, maybe, but you get the idea. So one of these hydrogens leaves with the water, and you end up with an OH and an H3O, right? Okay, so you're good. Here's what I need you to do then. Write the Kc expression for this equilibrium. You can't, because you're including the water by definition. So it wouldn't be okay to just put hydrogen here, because our reactants are water, and then it wouldn't balance. You don't have a source of hydroxide. Yeah. So guys, let's write the Kc expression. If this upsets you, be patient. Talk to me about why that's wrong. What's wrong with the H2O? Sure, there's two of them. That's fine.
You put the products on top.
Still wrong.
Units.
Why is it wrong? Say it again. Guys, water is a liquid. Water does not have a molarity. This is a heterogeneous equilibria. And we learned in the previous unit that when we write Kc expressions, we never include pure liquids or pure solids in the equilibria because they do not have concentrations. They're not dissolved. They do not have pressures. They're not gases. So solids and liquids never go in equilibria. Consequently, guys, these do not belong there. So the Kc expression for this, I can't back out that far. Guys, the Kc expression for this actually looks like this. So Kc is equal to, and you want to write this down because this is important. Kc is equal to this. The concentration of hydronium times the concentration of hydroxide. Don't miss this. This is interesting. So, let's talk logic, and then let's talk experimental data. First of all, the logic. Guys, what has got to be true of these two concentrations? What has got to be true of these two concentrations? I'm not talking math. I'm talking what has got to be true of these two concentrations. Right, because they have concentrations. But what has to be true of their values? No, guys, look, they're equal. Where does this come from? Where does the hydronium ion come from? From a water that loses a hydrogen. So if a water loses a hydrogen, it goes to another water and it makes hydronium, and then the one that got left out, the one that lost the hydrogen, comes hydroxide. So guys, for every one of these that gets formed, one of those have got to get formed. These have got to be equal, yes? Well, guess what? Chemists have done this. It's not hard. And it turns out that these concentrations in distilled water, these concentrations are equal. And remember, we're talking about distilled water, right? We're talking about water ionizing itself. There's nothing else there. This is just a cup of distilled water. And in a cup of distilled water, some water molecules are reacting with other water molecules, and they are turning into this. Do you understand what we're saying? Well, guess what? You can actually then measure the concentration of this. And when we measure the concentration of hydronium, what will it be relative to the concentration of hydroxide? The same. And guess what it is? In distilled water, the concentration of hydronium ion is 1 × 10⁻⁷ molar. Do you get it? Ah, pH. Guys, pH is the negative log of the hydronium ion concentration. And you may be able to do this in your head. What is the negative log of 1 × 10⁻⁷? 7. That's why the pH of water is 7. And again, guys, Daniel asked, why do we care so much about hydrogen? Why don't we do PN? Well, guys, our whole world is based in water, quite literally. And this is why we say that pH 7 is neutral. Because when water ionizes itself, there's nothing there but water. And water does that naturally, and it achieves a molarity of 1 × 10⁻⁷ molar hydronium ion. And hydroxide too, but pH is hydronium. And so, guys, this is why water has a pH of 7, because just sitting there all on its own, its concentration of hydronium ion, just a moment, is 1 × 10⁻⁷. Go ahead.
Is that at standard temperature? Because if you increase the temperature, would that make more ions?
Sure, because we understand, right, that equilibria are temperature-sensitive systems, so this is at 20 degrees Celsius. Yeah. You guys good? Now do this. So guys, if we take that number and plug it in right there, because this, don't miss this, this is the concentration of hydrogen. Guys, what will also then be the concentration of hydroxide? The same, right? Now do the math. What is 1 × 10⁻⁷ times 1 × 10⁻⁷? 1 × 10⁻⁴. And when we write it that way, this C becomes a W, and we now have a very powerful equation that you will find on your equation sheet. Go find it. You got it? So guys, on the back of our equation sheets under equilibrium, you'll notice 1, 2, 3, 4, 5 equations down, it says Kw, and that is equal to the hydrogen ion concentration. Notice here they left out the hydroxide. They are simply saying that the water's breaking apart. We understand that that hydrogen is going to another water to form hydronium, which may have been what you were getting at earlier. So guys, notice what we've got. Hydrogen ion concentration times hydroxide ion, not 20 Celsius, will be 1 × 10⁻⁴ at 25 Celsius. Do you see it? Because guys, this is a very, very powerful equation. Does it come up on this slide? No, it comes up on the next slide. So guys, this equation is going to be pivotal, no pun intended, to everything that you are going to do in this class. So guys, let's talk about this. What does this equation represent? Fundamentally, what does it represent? It represents the playground. Think about that. Guys, if you like this analogy that because all acid-base chemistry is in water, if you like that analogy that the water is the playground, and if you're comfortable with the idea that the water is no longer a passive participant, but the water is going to get involved in the chemistry like a playground playing with the kids. Guys, this is the equation that describes the playground. This is the level playing field upon which all acid-base chemistry is literally housed. So we have an equation that says we can now pin down definitively what the water is doing. If it's just water, if there's no kids on the playground, if it's just water, then this is going to be 1 times 10 to the negative 7th molar, and this is going to be 1 times 10 to the negative 7th molar. So if there's nobody on the playground, this is what this equation is going to do. Do you see what I'm saying? But guys, check this out. We also know the value of Kw, 1 times 10 to the negative 14th. Now let's talk. Does Kw change? It's a Kc value, right? Does Kw change so long as we don't change the temperature, change the surface area, or add a catalyst? Does Kw change? It doesn't. It is a fixed point. So guys, pause there mentally. Ready? Because this is going to be interesting, well, or at least critical. So guys, the idea is this. This equation describes the water in which all of our chemistry is going to take place for the rest of the year, forever. So this describes the playground. And here's what we know. If the playground doesn't have any kids in it, this is going to be 1 times 10 to the negative 7th molar. This is going to be 1 times 10 to the negative 7th molar. And then this doesn't change. So long as we don't change temperature, right? This value does not change. Can you picture it? Now let's put some kids on the playground. So let's come along and let's put some HCl kids in the playground. Well guys, what does HCl do? Gives away hydrogens. As the HCl on the playground gives away hydrogens, where do those hydrogens go? They go to make hydronium ion. So guys, what's going to happen to the hydronium ion concentration? It's going to go up. But this doesn't change, right? So if that doesn't change and this goes up, what does that have to do? Go down. So guys, understand that this bare equation that describes the playground is a fixed point. And then when we bring kids onto the playground and when we start doing chemistry, Kw does not change. And because Kw doesn't change, if we add an acid, this goes up. But that forces this to go down because Kw doesn't change. We're just shifting in equilibrium. And similarly, guys, if we add NaOH, that makes this go up. So what has to happen to hydronium ion? It's got to go down in order for the equilibrium to remain the same so Kw doesn't shift. So guys, this equation is going to be very helpful to us because if we know one value, we can then figure out the other value because Kw doesn't change. Does that make sense? Do you see where we're going with that? Okay, so guys, let me give you that in notes form to give you something to fall back on. But let me ask you a question first. Do you like the playground analogy or is it distracting?
That's good.
Is it okay? And maybe you won't know until you start, playing around with these. But guys, I find it very useful. So here's the idea. We know experimentally that Kw has a value. It's 1 times 10 to the negative 14th. But guys, understand, as we said, this relationship not only holds true for pure water, the playground. It also holds true for aqueous acid-base systems, the kids in the playground. So when we put kids on the playground, Kw doesn't change. Because Kw doesn't change, if we know the hydrogen or the hydronium ion concentration, we can figure out the other and vice versa. So I think about this, and forgive me, this is sort of stretching the playground analogy, sort of like a seesaw. So the idea is that if you think of this as sort of the fulcrum of the seesaw, and it's a fulcrum because kW doesn't change. So it's like this equilibrium is balancing on kW. As this goes up, this has got to go down, and vice versa. So it really is like a seesaw. It's a teeter-totter, and it balances on kW. Again, maybe taking that playground analogy and stretching it a little too far. You okay? Yeah.
So, if, I'm just wondering, like, about the increase in temperature. So if we're doing pH just on the concentration of H, so we're not thinking about the concentration of OH, if we increase the temperature.
Let's not, everything's going to be at 25 Celsius. We're not going to mess around with temperature changes because understand that changes kW, and so everything you're going to see, if you'd like to talk individually, I'd love to do that, but it's not pertinent to anything you're going to see in this class. Yeah, understand it's pertinent to the world in which we live, and all sorts of funky things happen as you change temperature, but everything we're going to do in here, kW is 1 times 10 to the negative 14th because we're always at 25 Celsius. Is that okay? So guys, this then becomes the interesting follow-up question, which we've sort of skirted around, but now we need to talk about it. So guys, the question then becomes this: how do we measure the hydronium ion concentration? We understand that in pure water, it's 10 to the negative 7th molar. We understand that if we add something like HCl, it goes up, and correspondingly OH goes down. But how do we measure it? Well, the answer is pH. So guys, let's remind ourselves about pH. Sheet, or it should be. Yeah, there it is. And guys, you'll notice that they give you another interesting term that we're going to talk about to wrap up the day. So guys, pH, you see it there, it's at 6 equations down. pH is the negative log of hydrogen ion concentration. But then notice, guys, we've also got pOH, which is the negative log of the hydroxide ion concentration. And I'll show you what that means in just a second. But guys, this is the way physically we measure these concentrations, is with a pH meter. Which means after the lab that we're going to do third period today, we're going to just get into a bunch of acid-base chemistry. And quickly, guys, I'm going to be checking pH meters out to you. I'll explain how they work in third period. But I'm going to be giving you digital pH meters that plug into our laptops. And for so many of the labs, the titrations that we're going to be doing will actually be measuring pH. Which makes it a little more interesting. So guys, what is pH? Well guys, pH, and I don't know if you need to write it down, you're welcome to if you want, is simply a mathematical expression of acid-base concentrations or strengths. Remember that low pHs are acidic and high pHs are basic. Do we need to talk about that more? Is that okay? Can you see it mathematically? I feel like I need to say it. So you understand, and it seems like maybe you do, because we did this. Guys, that the negative log actually just draws the focus onto that exponent. And because it's the negative log, it means that the negative goes away. So it's really, the negative log is just focusing in on this value, which is functionally telling us the size of the negative exponent. So the larger the pH, the bigger this number is, but because it's a negative exponent, it means the concentration's going down. Does that make sense? So why is it that the really high pHs are bases and not just really weak acids? I really want you to chew on this, guys. You should understand it now. Yeah, let me, okay, but good. But let me say it again. So we understand this, right? That the low pHs are the acids and the high pHs are the bases. But if high pHs, if you've got a solution that's got a pH of like 12, that is still 1 times 10 to the negative 12th molar what? Hydronium ion or hydrogen. So guys, with pH, the focus is always on hydronium ion. But at pH 7 and above, we say that those are the bases and not the acids, and we've defined bases as having more hydroxide. So how does that work if we're still focusing on the hydrogen?
Because as the hydronium, the concentration of hydronium goes down, the concentration of
Mm-hmm.
hydroxide goes down.
Good. Says who? Not KC, okay? Right. Guys, are you connecting with what Brandon's seeing? Guys, the idea is this. Hydrogen times hydroxide is Kw, and Kw doesn't change. So the way that this works is for pHs less than 7. So that would be 1 times 10 to the negative first molar up to 1 times 10 to the negative sixth molar. Those are high concentrations of hydronium or hydrogen ion. Those are our acids. Then at pH 7, which is 1 times 10 to the negative 7th, these two are equal. But then, guys, what happens at pHs above 10 to the negative 7th? Well, that would be 10 to the negative 8th up to 10 to the negative 14th. And now the concentration of this is below the concentration of just pure water. So the concentration of this is below 10 to the negative 7th. So if the concentration of this is low, what's the concentration of hydroxide? High. And that explains why pHs above 7 we consider to be basic, because very literally the concentration of hydroxide is greater than the concentration of hydronium, because the only point they're equal is at 10 to the negative 7th. Go ahead.
Did they come with the 10 to the negative 14th lab? Where did they come with that?
We could do it right now. Take a cup of distilled water, shove a pH meter in it. It'll be pH 7. So now that we know that the pH of pure water is 7, that tells us that this is 10 to the negative 7th molar. We know that that's the same, and 10 to the negative 7th times 10 to the negative 7th is 10 to the negative 14th. So we don't have a kW meter. We understand that kW is 10 to the negative 14th, but we don't have a kW meter. We have a pH meter, and then we can discern it from there. Go ahead, Kim. Oh boy, yeah. So when we say 1 to 14, I just throw that up because I think most of you are comfortable with that as the biologic range. But 1 molar, let's do this. So right, even worse, right? So pH is the negative log of hydrogen ion. So what if we have 1 molar HCl? Well, that would be the negative log of 1, which is what? 0. So the pH of 1 molar HCl is 0. Does that make sense? What if so 1 molar HCl has a pH of 0. What about 10 molar HCl? So what's the negative log? What's the negative log of 10? It's actually negative 1. So the 12 molar, let's do it really quick. So the 12 molar HCl, didn't we just use that in lab? Yeah, so the 12 molar HCl, so hold on, I gotta change the, okay. So the 12 molar HCl that we just used in lab has a pH of negative 1.08. So what's the extreme? Well, I've got sulfuric acid that's 18 molar, but its concentration of hydrogen is actually a little greater than that because it's polyprotic. So it's actually more like 18.1 molar. So take the inverse log. So that's got a pH of negative 1.36. So that would be probably the high end, well, the low end, the strong end. And then understand that at the other end, and I hate this stuff, actually worse than the strong acids, we're going to be, the first real titration that we're going to do in this class, we're going to be using 20 molar sodium hydroxide. Yeah, it's horrible. I seriously, it just makes me cry thinking about it. But you'll see why, but we're going to be using 20 molar sodium hydroxide. Yeah, it's awful stuff. Yeah, go ahead. Hold on.
So you have only one at like around 7 pH range. So how do you know when it's like what's super early? I don't know. It seems like the logs harder. Like the lower you go, the harder it is.
I don't know what you're basing that on. I mean, are you...
So it's like 7 is normal, but like so does 2.
Mhm. thereabouts, 2 to 3, yeah. Uh-huh.
So, but that doesn't seem to hurt. But we can get down to like -1. But that's just because it's law. You know, like law.
No, I understand what you're saying. Yeah, so you let me do this maybe, Brandon. So guys, if I understand correctly, you're just trying to contextualize this and go, okay, but what about? So let me offer this perhaps as a place to talk. So like so. And let me get in writing mode. What would be a good color? Green? All right, I'm going green, but I hate it. So, Brandon, maybe here are some things that we can talk about. So, one thing that we've got to talk about first is this. Say that you've got, for example, Coke or vinegar, both of which have a pH of 3. So what does that mean? Well, it means its hydronium ion concentration is 10 to the negative third. Okay. But also understand those are both weak acids. And again, you're not confusing weak with concentration. You're confusing, I'm sorry, you shouldn't, not you. We need to be careful to not confuse the word weak with not corrosive, right? So when we say weak, it means that whatever it is, whether it's the acetic acid in vinegar or the carbonic acid in Coke, that thing is a weak electrolyte. So not all of it broke apart. And understand, biologically, that's important. That if you've got a weak acid, it means that waiting in the reserves are these conjugate base ions that can also do chemistry, right? With the strong acids, they're there, but they're not reactive, and consequently, it's a whole different game. So biologically, and frankly, even if we wanted to, I couldn't explain why. Not all pHs, not all things with pH 3 mess with us the same. And I think that's sort of what you're getting at, maybe. Yeah, and so understand that to look at this and go, oh, pH 3. Okay, so I can drink Coke and I can drink vinegar, but also pH 3 would be 0.001 molar HCl, and consequently I should be able to drink that too. Did you see how I did the math? So this is 1, 2, 3, which would be 1 times 10 to the negative third written in scientific notation. So Coke and vinegar and 0.001 molar HCl all have the same pH, but you wouldn't want to drink that. So it's not that simple. That said, if you've ever drank large quantities of vinegar, you'd get sick too. But understand that the biology of the chemistry doesn't map as simply as just a number makes it okay. Does that make sense? Go ahead.
I have 2 questions. So the first is, can you only do that complete conversion of molarity equates to pH or vapor HCl?
Mm-hmm.
It's a strong base acid.
Yeah, and so can I pause there for a second? Guys, did you hear what Matt just said? This is important, but not today, but it's going to become very important. So this math that I did right here, where knowing the molarity of the acid then allowed me to quickly figure out the pH, this only works with strong acids. Why does this only work with strong acids? Because they're the only ones that completely dissociate. So what about this? What if we had 0.001 molar acetic acid? Well, acetic acid is a weak acid. It doesn't completely dissociate. As a result, would it be more or less acidic than hydrochloric acid at the same concentration? Less acidic. So how could we then figure out the pH of this? Icebox. Let that rattle for a second. Because guys, that's what we're going to do next time, is figure out the pHs of these solutions, which Kami is making me realize we're not going to talk about why HF is a weak acid and HCl is a strong acid. I forgot we've got to do icebox for weak acids first, so that'll be next time. But guys, understand that's why we taught you iceboxes. The real application to iceboxes comes with weak acids and bases. Is that okay? Okay. So guys, with that said, let's look at this. So Brandon, do you feel like we satisfactorily addressed your thoughts? Okay, so let's do this thing, guys. Let's look at extremes. So let's go down here. Let's go stomach acid and let's just call it pH 1. So from the fact that stomach acid has a pH of 1, are you okay with this idea? That we then know that its molarity is 1 times 10 to the negative first. You write it as a decimal, that's 0.1 molar. Is that okay? Okay, now let's go to the other end. And guys, let's go all the way up here and let's just do pH 13, which is 0.1 molar, 0.1 molar sodium hydroxide, which is functionally like oven cleaner. And guys, we understand that this 0.1 molar is actually this. That is the concentration of hydroxide. Let me zoom out. I want to keep that top part as well. So guys, that number is the concentration of hydroxide. But now guys, check out all the interesting relationships that this creates. So this is 0.1 molar sodium hydroxide, which we then understand is 1 times 10 to the negative first molar in hydroxide. You okay with that? Now we're talking hydroxide concentrations. But guys, here's the thing that's interesting. This has a pH of 13. This is where the teeter-totter comes into play. Because guys, if the molarity of hydroxide is 10 to the negative first, remember this, if the concentration of hydroxide is 10 to the negative third or first, remember then that the concentration of hydrogen ion has to have a proportional decrease so that Kw doesn't change. So if this is 10 to the negative first, the hydrogen ion concentration is 10 to the negative 13th. And that would give this a pH of 13. Do you see how that works? These balance around pH, around Kw. So if we go down here, this one works too. If stomach acid has a hydrogen ion concentration of 10 to the negative first, it will have a hydroxide concentration of 10 to the negative 13th. Again, multiplying these two together, just like multiplying these two together, has always got to result in 10 to the negative 14th. Do you get the idea? Now guys, check this out. We understand that pH is this, right? Is the exponent, sorry this is low, but pH is the exponent from the concentration of hydrogen ion. Well, guess what? We can also do pOH, which is the hydroxide ion, the negative log of the hydroxide ion concentration. So now we've got this new interesting value. So we can talk pH when we want to focus on hydrogen ion. We can also do pOH when we want to focus on hydroxide ion. Same equation, we're just looking at hydroxide. So now do you see all the interesting interactions between these two? Do you see it? Because let me clean up my mess and check this out. And this is where we're going to wrap up today. So guys, let's do this. If we put the world's longest multiplication sign down the middle, what will this column times this column always result in the product of? 10 to the negative 14th. So guys, these two together will always give us a product of 1 times 10 to the negative 14th. That's the whole idea with that Kw equation. But now guys, watch this. Grow out from the middle. And this is where this gets interesting. You came in here understanding that pH is that exponent. pH is that exponent. pH is this exponent. And that works all the way up, right? But now, guys, we brought into this conversation pOH, which is now this exponent as we talk about hydroxide ion concentration. And because of the autoionization of water, we know that 7 is the balancing point because that is the pH of pure water, right? So now, guys, let's have this other conversation. So again cleaning up my mess, in summary, here's what we know. These two columns will always do what? Multiply together to give you 10 to the negative 14th. But guys, what about this column and this column? They will always add up to 14. It's just a log problem. But guys, that will also always be true. If you know the pH of the substance, you also know its POH, because that will always add up to 14. So guys, let's grab those interesting realities out of our equation sheet. Yeah. Do you see it there? So let's summarize everything that we've talked about. So guys, you've got those first four equations, which are Kc values. Well, top is Kc, then Kp. We're going to talk Ka and B later. But now, guys, take a look. We now understand what that Kw means, right? Hydrogen times hydroxide will always be 1 times 10 to the negative 14th. You'll notice below that we've got a Ka, Kb thing. We'll talk more about that in a couple days. Then below that, we now own, I hope, pH is the negative log of hydrogen ion. Notice that we could also put hydronium ion there as well, depending on whether or not we want to include the water. But then on the other side of that line, we've got POH, which is just the negative log of hydroxide ion concentrations. And then as Matt said, you know, using our logarithm chops that we learned in secondary 2, or whenever, we can then also say that POH plus pH is 14, which is just taking that upper equation and bringing it together down below. So guys, these are all now tools that you are going to use reflexively throughout the remainder of the year to convert between pHs and POHs. Do you get the idea? Okay, so guys, with all of that said and done then, there's one more thing that we need to talk about, and it's frankly what Matt just said, and then we're ready to wrap up the day. So guys, it goes like this. Really, all I need to know is that you're okay with this. In the case of strong acids, the concentration of the acid is equal. Is that enough for you to go, yes, that's true, and I understand why? So what we're saying is this. If we have a beaker full of 1 molar HCl, how much HCl is in that beaker? None. If you have a beaker full of 1 molar HCl, you ain't got any HCl. What do you got in there? You've got 1 molar hydrogen ion, which is actually hydronium, and then you've got 1 molar ion solution, right? HCl is a strong acid when it goes water, it dissociates. Every one of those put in makes a hydronium ion, chloride ion. So in 1 molar HCl, the concentration of the acid is actually the concentration of the hydronium ion. You good with the idea? Okay, so guys, what about this? What if we've got 1 molar acetic acid? What's in that beaker? Everything. Because guys, the chemistry that's taking place is this. And let's include the water. And this forms that's the reaction. So guys, when we put this in water, do we make some hydronium ion? Yeah, it's a weak acid. For every hydronium ion that we make an acetate ion, which is the conjugate base. But guys, this doesn't go to completion, which also means we have acetic acid molecules. Now guys, where are the acetic acid molecules? Dissolved in the water. They dissolve, but they don't dissociate. Remember, we talked about those being different and possible. So guys, all of this dissolves in water. So if we could look inside of this solution, we would have some of this, we would have some of this, and we would have some of this. But how much hydronium ion would we have if we started with 1 molar acetic acid? Less than 1 molar, because it's a weak acid. What is it actually? Because we're going to calculate that next time in class, again using ice boxes. You're going to find out that it's disappointingly small. Don't quote me, but, well, quote me. I think this is right. I think this is about 5%. I think it's about 5% dissociated. We will actually calculate what are called dissociation percentages next time, but I think that acetic acid is at about 5%, which means 95% of the acetic acid molecules are still there intact. Yeah.
You need 20 molar of that to be the same as 1 molar.
If those numbers hold true, yeah, which would obviously be impossible and horrible on a salad. You guys good? All right. So guys, let me throw this your way. And here we go. There's your homework. Yeah, you got this last time. So guys, before I stop recording, hey, little disclaimer. Not a disclaimer. Just need to talk. Guys, first of all, we trust one another, right? You trust me enough to know that I would never give you busy work. I respect you and your time more than that, and I think I've demonstrated that to you repeatedly throughout the year. That said, guys, there's a lot of homework in this unit. Not more than there should be, but there's a lot of homework. You're going to see that and it tapers off in chapter 20. And there are some days, even in this unit, where it won't be this much. But this is a lot. And that's okay. Because, guys, if I were to cut this assignment back, it wouldn't be complete enough. And so, guys, I say that to say, as you are budgeting your time for the next 2 to 3 weeks, budget a little more time for homework in this class. Because the assignments are going to be a little more extensive. So.